Okay, so there we go. Quick. So section 3.5, it's so minor. I mean, it's really, there's almost nothing there. I gave you a few problems to do, but there's barely anything there to do. There's really just two new reasons we get on that purple sheet, and they're these two. Transitive property for parallel lines. Now, real quick, when we say the word transitive, that's an important word in math. Think what it means to be transitive. Transitive, the classic example of transitive is this one. If A, transitive property of equality, if A equals B and B equals C, then what? A equals C, exactly. So the transitive property literally like transfers whatever property you're talking about from one thing to another thing to a third thing. So it transfers it through a middleman, right? So if A is equal to B and B is equal to C, then we're transferring the equality from A through the middleman B all the way over to C, right? That's all it is. This is kind of the same type of deal, isn't it? If two lines are parallel to the same line, then they're parallel to each other. So for example, if P is parallel to Q and Q is parallel to R, then doesn't it make sense that P must be parallel to R, right? So that's the transitive property for parallel lines. Not a big deal. Just very similar to that, slightly different but very similar, is the transitive property for perpendicular lines. Now this one says that as long as we're in a plane, then if two lines are perpendicular to the same line, they must be parallel to each other. Doesn't that make sense? If M is perpendicular to P and N is perpendicular to P, then M and N must be parallel to each other, right? Okay, so there's the other one. Not a big deal. That's all I'm really going to say about that for now. Let's talk slope for a little bit. Okay, so we know that slope is the slantiness of a line, right? We calculate slope by finding rise over run, right? And we've got a couple ways of representing that. So let's take a look at a specific example here. I'm going to change this ever so slightly. Oops. I'm going to make this, how about a 6? Okay, so let's take these 2 points, and I want to do 2 things here. I want to illustrate a really important point. This is, pay very close attention to this, because this is a classic place where people tend to make mistakes. Let's do 2 things with this. Let's calculate a distance, and let's calculate a slope. Okay, first of all, remind me real quick, what is our distance formula? D equals what? Square root delta x squared plus delta y squared. Okay, so let's actually calculate a distance. Let's calculate the distance between A and B, which we would, in geometry, we would just say that like that, wouldn't we? It means the length of segment AB, or the distance between points A and B. And so what do we get then? Square root of, what's our delta x going to be?
16.
I think I heard, what's delta x?
16.
Okay, you're squaring it though, right? So delta x is 4 squared. How do we get to 4? Well, 6 minus 2, right? So 6 minus 2 squared, which is the same thing as 4 squared. What about the delta y?
3.
Okay, we got 3, didn't we? Right? And the reason we were able to do that, technically the answer is negative 3, right? But we always said, well, let's just take the bigger one minus the smaller one so we could make it positive. But there's something going on there I want you to be aware of. Technically, it's 1 minus 4, which is negative 3. And we always just said, well, okay, as long as we're squaring it, if I square a negative, what always happens? I get a positive answer, don't I? Right? And so it's much easier to square a positive. So instead of squaring negative 3, we always just instead squared positive 3, because we know we're going to get the same answer. That's a great idea. Let's kind of refine the way we talked about that though. Whenever we, rather than, now that we're moving on a little bit, rather than always thinking about delta x and delta y as being the bigger minus the smaller, the reason we're able to do that here is because they're being squared. Instead, let's say this. Whenever we ever, at any time in math, in any possible situation, if I square a negative, what should I always do? Square the positive. Always just square the positive instead. When I look back at the, and I do this, when I look back at the Moodle results on that chapter 1 test, for all of the times that questions about calculating distances or lengths of segments or things like that, when they were missed, I want to say probably 95% or more of the time, probably even more, it was mistakes were made because people squared a negative and they didn't put parentheses around it. And remember, with any calculator, you must put parentheses around a negative if you're going to square it, and that's hard to remember. And so for that reason, always, if you're squaring a negative, never even type the negative sign, just square the positive, right? So our result ends up being square root of what? 16 plus 9, square root of 25, which is what? 5. So we get a distance of 5, right? Okay, now let's talk slope. Okay, slope is just, it's a little bit different. You'll tell me why. What's our formula for slope? What variable do we use for slope? It's a little weird. Y, say it again. Y equals mx plus b, you're saying. Yeah, there's slope in there. I'm glad you said that, because what's the variable that represents slope? M. I can't even remember why. I think it's a French word or something. But slope, M represents slope. We know it's rise over run. And we, in terms of, what's a math formula for that? Okay, so we could say y2 minus y1 over x2 minus x1. Or if we want to, we could even call it delta y over delta x. That's really all that means, except this time it's different. Are the delta y and the delta x being squared in the slope formula? They are not. They are in the distance formula. So go ahead. So it can be negative, right? A negative answer now is different. It wasn't with the distance formula because we always squared it, so it didn't make any difference, but now it does. Now we do have to be careful about the sign. So when we calculate a slope here, what are we going to get? Using our points up here. What minus what over what minus what? Okay, so we're going to get 1 minus 4 over 6 minus 2. Everybody see that? Okay. 1 minus 4 over 6 minus 2. So that's fine. So what we said there, what was implied was, we're going to call this one 0.1 and that one 0.2, and we always subtract the values of 0.1 from the values of 0.2. We have to be consistent, right? So if we subtract the 4 from the 1, then we must subtract the 2 from the x, right? And that gives us on top what answer? Negative 3 over 4. So we get negative 3/4. Okay. If I divide a negative by a positive, we just get a negative answer, right? Could we have done it differently? Yeah, we could have. We could have, if we wanted to, we could have called this one 0.2 and that one 0.1. It would have worked, right? Then we would have gotten what minus what on top? No, on top. 4 minus 1. Y2 minus y1 would have been 4 minus 1 divided by, not 6 minus 2 this time, 2 minus 6. Right, and that would have given us 3 divided by negative 4, agree? And if I divide positive by negative, I get negative, right? So either way, I get negative 3/4. Okay? Now, is there a preferable way to do this? I would say slightly. Which way do you think is probably better, the red or the green? Red.
The
The red, yeah, it is. How do we know how to get the red one instead of the green one to start with? Well, here's the hint. What you can always do when you want to assign a number to the points, you always want to pick the number with, the point with the smaller x value should be point number 1, right? Not point number 2. Because 2 is less than 6, we'll make this one 0.1 and that one 0.2. On a graph, what does that mean? If the 2 points are kind of plotted on a graph, one of them is going to be further to the left and one of them is going to be further to the right. Which one should be point number 1? Further to the left. Yeah, further to the left. And why do we say this? It's not a huge deal because we got the same answer either way, but once again, it's easier to make a mistake if you have a negative number in the denominator instead of the numerator, right? It just is. I'll tell you, guaranteed, after having taught math for a long time, that is a source of error sometimes, is when you have the negative number on the bottom. So if you have a choice, you might as well do it the same way every time. Just always pick the bottom, pick the numbers so that you're going to get a positive number on the bottom. Meaning, so that point number 1 is the one with the smaller x value. It'll work either way, but I just recommend that way. Okay? Questions? It's all kind of review. All makes sense, right? If we want to look ahead just a little bit here, so what about this? Well, what do we know then about parallel lines? We can skip this. We just did one like this. What do we know about parallel lines? If they must have the same slope. Doesn't that make sense? Because they have the same slantiness, right? If they're parallel, they have, to use a real technical term, they have the same slantiness, right? So they must, that means slope. They must have equal slopes. I don't know why these things got so messed up, but they sure did. So the slopes of parallel lines, the definitions of slopes of parallel lines on our purple sheet just says, in a coordinate plane, if two lines are parallel if and only if they have the same slopes. Okay? Those things go together. Let's take a quick look at, just ignore, that stuff didn't work very well, but we'll just look at this part of it. Let's look at these 3 lines, and let's determine if any of these are parallel. How are we going to do that? What do we have to compare in the lines to see if they're the slopes, right? That's all we have to do is compare slopes. So if we look at these 3 lines, let's look at the green line, the red line, and the blue line. Let's calculate a slope of each. So it looks like this is supposed to be graphed on a plane, and if you look at these 2 points on the green line, one of them seems to be, if that's -5, so it must be back 6, so the x-coordinate's -6. And the y-coordinate looks like it's 5, yeah, +5. And then this one right here is at, looks like -4. And then what's the y-coordinate? If it's on the x-axis? 0, good. Okay, so let's calculate that slope. The green slope is what minus what over what minus what? What's going to go on top? Which one am I going to call point 1? Yeah, the left one, right? Because this one's further to the left. So that one's point number 1, and that one's point number 2, right? So then what's the rise? What minus what? Yeah, good. So y2, right? 0 minus 5 over the run would be -4 minus -6. Well, what's that give us on top? -5, and on the bottom, what's -4 minus -6? +2. Good. So we're adding 6. So there's my green slope, -5/2. Let's calculate the red slope. So the red slope, it looks like we've got points at, what, -2, +6? Does that look right? And what's that one going to be at? No? 0, 1. Good. So the red slope would be what minus what on the top? Okay, good. y2 minus y1 divided by 0 minus negative 2. So what's that give us on the top? 1 minus 6? Negative 5. 0 minus negative 2? 2. What's that tell us about those two lines? They are parallel. Okay, how about the blue? Okay, so the blue, we got point, these are easy ones. What's that point? 0, 6. What's that point? 2, 0. Good. So then the blue slope, I guess we'll go right there, equals what minus what? 0 minus 6 over 2 minus 0, which is just what? Negative 6 over positive 2. What's that equal to? Yeah, negative 3, isn't it? Same thing as negative 3 over 1. So what's that tell you about the blue line? It's not parallel to either of the other two. Good. So only the red and the green were parallel. Okay, last issue, and then we'll be done with this. Oops. Where are we here? Oh, okay, that's terrible. Okay, let's just. I don't know why this thing got so messed up, but I'm just gonna copy this and we'll do this on a separate place. This is what I want you to be able to do. And this is kind of an important one. Okay, so write an equation of the line passing through the point 2, 3 that has a slope of 5. Okay, so let's remind ourselves how we do this. So first of all, when we want to write the equation of a line, in what form are we going to probably write the equation of that line? Mx plus b, good, so slope-intercept form, good. So we want to write this in the form y equals mx plus b. So what are the only two values I have to be able to plug in? M and b, right? M is the slope, b is the what? Y-intercept, okay, good. So, well, it's that too, same thing. We might call it the start value. It's in a story problem. So y equals mx plus b. So are we given any of that stuff up here? Yeah. We're given what? Slope. So this tells us right here that m equals 5. What's the only thing we have to find? Yeah, we got the y-intercept, right? So we've got to find b. Now, how am I going to find b there? If I know, and you got to be a little bit careful with this, m and b, and just bear with me for a second here. I want to this is an interesting point. It's a subtle distinction, but m and b are what we call parameters in math. What that means is we could create any possible line in the entire universe, as long as we're talking about, on a plane, any possible line in the xy plane. We could create that by just dialing in two numbers, the value of the slope and the value of the y-intercept, right? If I dial in those two numbers, I'm going to get a unique line, and that's all it takes. Once I have dialed in those numbers, let's just say that the slope is 2 and the y-intercept is 3, whatever. How many values of x and y are on that line? What do you think? If I were to graph a line, lots, yeah. So I said slope of 2, y-intercept of 3. So then my y-intercept is right there, and my slope, I'm going to go up 2 and over 1, right? Oops, hang on, what did I do? Messed that up. My y-intercept is 3, I said. I don't know why I put it in that spot. I gotta go back a little bit. Stop. So my y-intercept is 3. It's gonna be right there, isn't it? Right? If I write the line y equals 2x plus 3. So there's my y-intercept. I go up 2 over 1, create another point, and there's my line. That's always how I graph lines, by the way, if you remember back to our review. We always start with an anchor point and use a slope triangle to create a second point, connect and extend forever, right? How many x and y values are on this line? Infinite, right? There's an infinite number of points on this line, and each point has an x and y coordinate, right? How many different slopes and y-intercepts are on that line? One, right? The line has a single slope and a single y-intercept, right? So the slope and the y-intercept are not variables. Once we have the line, once we have the values of m and b, that represents the line. Now x and y are variables though, because x and y can both vary on this line. Does that make sense? One value that they could have is 0, 3, but they could also have the value 1, 5, or an infinite number, another infinite range of other possibilities, right? So they could be all those things. But if we know one point on the line, that's a value of x and y that work, right? On this line, for every x value, there's only going to be one possible y value that works. There's an infinite number of x values and a corresponding infinite number of y values, but they go together very specifically, right? So if I have one of those points, that's telling me a value of x and y that work on the line. Does that make sense? Right? I know that when, if this is a point on the line, I know that when x equals 2, y equals, on this line, 3. Yeah, guaranteed, because that's a point on the line, right? So now if I want to go back and solve for b, I want to know what b is. What's my strategy? Any ideas? Plug them in, right? I know values now of m and x and y that work on this line. The only thing I'm missing is b, right? It doesn't matter that x and y are variables and m is a parameter. I can still plug them in because these x and y values I know go together, right? So if I plug those in, what do I get? Well, 3 goes there because that's my y value. 5 goes there and 2 goes there, right? Plug that stuff in and what happens? I get 3 equals 5 times 2 plus b. What do I have to do to solve for b? It's not hard, right? What do I do? Multiply 5 and 2. And then subtract 10. I just have to isolate b. So the 10s go away. I get b equals what? -7. And now I'm done. Now I know both the values of b and m, and so I could write the equation of the line in slope-intercept form, right? So what is the equation of the line then? Y equals what? What's m? 5x minus 7, right? So I found the values of m and b, which identifies that line, okay? Is it confusing that you write this with x's and y's instead of 2's and 3's? Okay, I mean, if it is, just remember that the 2 and the 3, those aren't permanent values. Those are just example values that work of x and y, right? But the 5 and the -7 are permanent values for that line. And so we got to write it with only the permanent values written in there, and the x and the y we have to write as variables, right? They just go back to x and y. Make sense? Okay? I think that's good for today. Grab Chromebook and get cranking.
Can I go to the bathroom?
Yes, you can.